Uh, Good evening, everybody, and welcome to week 9 problem solving session. And it's a last session, and in this session, I will be solving questions related to from week 1 to week 4. Yeah, from week 1 to week 4 because of the questions which are related to this weeks are numerical based, and that will help long run. It will help you to solve this kind of a problem. Yeah, I mean, like there are some problems with and all those. There is a problem on Jacobian uh, palette kinematics problem, phase transformation, phase parameters. So we will try to solve those problems so that we'll do a kind of a revision and will also increase your and because I will be solving some example problems, so it will help you to understand the concept more. Let's just dive into. So the first question is it's regarding the transformation, homogeneous transformation. So let's read out the question. Consider a rigid body with a reference frame B affixed to it. Initially, the body is placed with frame B aligned with the world frame. So world frame is a fixed frame. The first body is typo here. Is transfer. So B is your body, and it is being translated by one unit along the vector. Vector is given here of the frame, and it has been translated by one unit and subsequently rotated in the rotation operator R. So this is the R. So first there is a translation by one unit along this vector and then a rotation which represent rotation about the some axis in A. Okay, so A is a world frame which is a fixed frame. Compute the homogeneous uh, transformation metric TB with respect to A for both cases. Okay, so there is only one case, so this part and obtain the coordinate B in A. The coordinate in frame B are this is in coordinate B. So there is a rigid body with a reference frame B. So B is your world frame. Okay, B is fixed frame, whereas is moving with A is moving with this transformation, right? So A is a moving frame and B is your fixed frame for world. And you need to tell me what will be the coordinate transformation matrix and also this is this coordinate is in B and how it will be so how it will be located in when we see it in when we see it from B when we see it from uh, frame A. So what will be the location, right? So first we need to do a translation. So this is your something like a world frame. Okay, and first what is happening is we are translating thing. Okay, so how much translation is happening? There is a translation of one unit. This is a vector, but this vector is not a unit vector, right? Right. So because it is given that it has to be translated by one unit. Okay, so you just can't write it. So like let's say you are in origin. So this is the origin of A initially, and when you translate right along this vector, you can't just translate one one one. Can't do that, right? Because the magnitude should be 1, right? If you have this, it will be root 3. The magnitude is root 3. So what you need to do is you need to normalize this vector. So the normalization part is 1 by root 3. This is the normalized vectorial direction. And you need to multiply it with 1 so that you get the new vector, which is this point. So So now after translation, your new position is this point, and the next point, next you need to do is you need to do some kind of a rotation. This is a rotation matrix. So compute. So the first part is compute the homogeneous transformation matrix here. Okay. So you can do it in two way. You just need to split this transformation into translation and that translation and rotation. The first part will be, so since this is a you're translating with respect to, let's say, a fixed frame, then you should need to pre-multiply stuff. Okay. First first what is happening? We are having first what it is happening. So which will represent rotation about some axis in A. So they are first rotation is happening here. So what we can do here is first you need to do a translation, then you need to do something like a rotation. The translation would be look like something like, because in first transformation you're not getting stuff, and it would be 1 by root 3. This is your translation thing which is happening. Okay. And you need to pre-multiply with your rotation matrix. This will be a rotation matrix, right? And this, there won't be any translation. This is the one way to do it, and the other way is first you get this rotation matrix, right? First you get this rotation matrix, and what you should do is, like, you have this vector here, right? You translated some at some point, and after translation you need to rotate stuff, right? So how you rotate stuff? So you have this. So this is your new vector, new origin basically, right? This is your new origin. So OA is your OA is your world frame, and OB is your, this is OB now. Okay, this is OB now. This is OB now, and after this you are rotating about some axis. You don't know the axis, but that axis is related to the fixed frame. That's why you are pre-multiplying. So you need to pre-multiply stuff. So what you are doing is you have this coordinate in position E frame, and you need to rotate this thing, right? How much rotation is to do? You need to do this. There is a matrix here. Just pre-multiply this, and this is what you. So this is your updated translation after rotation. And finally, so this is the translation part you calculated. This is a translation part which you get from here, and the rotation part remain the same. Okay. So I repeat again. So you can do this in two way. What you can do is, so instead of doing this, what you can do is you should multiply all these things. So what you need to do is, since the first operation there is no translation, 1 1 1 0 0 0, write a transformation matrix, and in the sec you need to pre-multiply with rotation also. In the rotation matrix, the translation part will be 0, and the same rotation part will come here. You can do this. So you can do this way also, and by this way also. There are two ways you can choose it. This is question one, and there is one more question on transformation. Let's read out what the question says. Compute the transformation matrix from end effector frame to the world frame. So this is your world frame which is given here. Okay, 0 0 0 x0. So this is x0 z0, and this is y0. A block marked with diagonal lines can slide. This block can slide in this. So how? So at an instant it is sliding. It is sliding at a distance d. While the shaded link, so this is a shaded link, rotate about z2 axis. where the Z2 axis is. This is the Z2 axis here. It's been shown. Assume that angle between y, I think it's, well, I think. So it is talking about the angle between y2 and y1, I think, and x x1. Okay, I need to paraphrase this. Okay, so you need to calculate a transformation matrix from going from this frame to this frame. Okay, so how you will do it? You need to do it step by step. So first you need to see what is happening first. So first you see translation is happening, and you go from zero frame to one frame. What you need to do? You need to translate by a distance d, right? But you need to also see that the frame itself is rotating. See, this is x naught frame, this is x1 frame, but you see the z1 frame and y1 frame, it's not aligning with x naught frame, right? So there is some rotation is also happening here. Okay, so you can see that the translation is happening, which is a d distance, right? But you need to also rotate stuff, right? So how should you reach there? So let's say if you rotate anti-clockwise, think anti-clockwise, yeah. If you rotate anti-clockwise along z naught x naught axis, this will be a new frame, right? So you need to translate and rotate stuff along x naught direction. So this is your first. So when you go from 0 to 1, this will be your transformation matrix. This is since you are, so this is your yeah, your translatory vector, right? 0 is for the x direction, there is no translation. But in y direction, you see there is a d translation. So there is a d term, whereas this term is a rotation part, right? So how you get this rotation part? You need to remember that 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 Rx, Ry, and Rz, those rotation matrix along those x-axis. No? So since we are rotating it along x direction, it will be something like one this, right? This s s is c is cos theta. This is something, yeah. So here we are rotating at I think, yeah. So we are rotating minus 90 degree. You see, okay. So you see, you can apply a something like a right hand rule, but you will get there. Okay. So it's a minus 90 degree. So there is a minus 90 degree rotation is there. R x minus 90 degree rotation is. So when you put like sine 90 degree minus sine 90 degree, it will be 1, and cos 90 degree, cos minus 90 degree is 0. Then sine minus 90 degree is minus 1. So in this way, you will get A, right? And then come. So when you go from let's say 1 to 2, what transformation you need to do? So when you go from 1 to 2, uh, you can see that along x1 direction you need to translate by A, right? And when you compare x1 frame of frame 1 and frame 2, you will find that there is a rotation is happening. Some sort of rotation is happening here, right? So what kind of rotation is happening? You need to also look into that. So first you can see that uh, yeah, first you see that there is a translation. So there is a here which has been already shown here, but you will see that this Z2 axis, there is a this is a X1 axis. So there is some sort of rotation is happening here. Okay, so the frame is not aligned, and also you can see there is some kind of a theta angular thing is also going here. So we need, there are two rotation which is happening here. So when you go from here to here, how to reach from here to here? So first translation which has been given here, but you can see there is this a rotation thing is happening here, but how to do it? So first we see what is happening here. So you can see Z2 is there, right? So, so let's say if you rotate along Y1, right? You need to apply some kind of a right hand rule, and let's say you rotate, let's say you let's say you rotate along clockwise along y1 direction, then your z1 will be aligned to z2, right? First rotate along y direction, right? Okay, so rotation along 90-degree, and then there is always a theta direction, right? So I think there is a theta, so this is the theta which I was talking about. So after aligning with z2, after aligning your z1 with z2, you need to also rotate stuff. So how to rotate stuff? It has been written that there is an angle. There is a angle between y1 and x1. I think be y2 and x1. I think something like that. So so what you need to do is like along z2, there is some kind of a rotation is happening, which is a theta direction. So first you need to rotate by 90-degree, and then along z2, thing along z2, because z2, so this axis remain the same, whereas this axis and this axis is not aligning. So there is a rotation along Z2. That's why I was this. There's something like R Z theta. Okay. So when you combinely multiply this, you will get something like this rotation matrix. Okay. And since you already know that your translation, so this is going from. So this is a transformation from second frame with respect to the first frame. And lastly, what you need to do is you need to now to go from second frame to third frame, you need to translate along L. So L is along y1 direction. So you see there is this y1 direction, and you need to see the frame here. So you can see that there is a frame change here. Okay, and if you look closely, there needs to be one frame which can change. So I think Z2 and Z3 is aligned. So yeah, but how to do that? Two is aligned. What you need to do is so here what we are need to change something. Yeah, so y2 is not here. This is x1. So you need to again rotate stuff by 90-degree. But what to rotate and how to rotate it? Okay, so you can see if x2 is something, but x2 you can see x, because when you rotate something like here, you can see the x0 and x1 this remain the same. So that's why you know that okay, there is this long x1, it is rotating. If you look here, I think it is rotating along z3 or z2, right? So if you rotate, let's say uh, by 90-degree. Okay, so when you rotate by 90-degree, this x2 will goes here and y2 will goes here, right? So there is a rotation of along z by 90-degree. Okay, and then there is a translation which you already know, which is L. Okay, so in this manner, you can get both of these three transformation matrix. Okay, and you can get a homogeneous transformation matrix. So from going from the base frame to the third frame, just need to pre-multiply all this manner. You can easily get an answer. Okay, so this is it. This is question number two. Coming, okay, I think I've not. Okay, so let's just look into the question number three. So it's related to Euler angles. So list all the possible set of Euler angle we discussed in class, which is Z, Y, Z. I think, is it possible to make Z, Z, Y Euler angle Y, or why not? Find the rotation matrix corresponding to the set of Z, Y, Z Euler angle, which is pi 2, 0, pi by 2. What is the direction of x axis related to the base frame? Okay. We need to find the rotation matrix first. But first we need to give all the possible set of Euler angles. So these are the possible set of Euler angles. There are basically 12 possible set. So you can repeat stuff. Let's say y, x, y, but you can't like repeat the same axis consecutively. Like you can't just say y, y. Let me see y. So there are, so you can make this like yeah, so you can make this n number of permutation and combination, and you will get, there can be only 12 possible sets of Euler angle. Let's see why we can't club two axis rotation together. So let's say if we are doing, let's say z z x, and we are saying it is not possible, why it is not possible, we need to do that. Okay, we need to do the Euler angle. So Euler angle, so we need to do the transformation and see why it is not happening. Since this is an Euler angle, so which means that uh, your moving frame, all those transformation has to happen along your moving frame, not respect to the fixed frame. So this is your fixed frame. Let's say add x, y, and y, right? And when you do something like a transformation here, so it is z, z, y, right? So first we rotate along this, what saying, we do something like this rotation, which is theta here, and then we again do something like a phi here. Because the Euler angle, it needs to be post multiplied. Okay? Not it's not rotating with respect to a fixed frame. And then there is a one more rotation which is happening at x, which is phi rotation. So when you do this matrix multiplication, you will get something like theta plus phi. So there is no so there is no independent rotation. So actually you are rotating along the same frame, right? Which is theta plus phi. There is only two independent rotation, but when you say possible set of Euler angle, it needs to be three independent rotation. Okay. That's why you can't club it. What is the direction of related to the base frame? Okay, so first we need to use this Euler angle, which is pi by 2, 0, pi by 2. So you need to do something like this. This is pi by 2, and this is 0 axis, and this is again pi by 2. So since this is a 0 matrix, when you put those equation, you will get I matrix. Is your it's a, yeah, it's a diagonal single diagonal element matrix. And when you do this thing, because since this z and z are along the same direction, you can club it, and this will be your pi direction, right? So when you rotate along, let's say this is your rotation, and you're rotating along z direction, and you're rotating along 180 degree. What you are doing, this is your y, and this is your x, right? When you're rotating along 180 degree, will happen, you get something like this will be your minus y, and this will be your minus. So what is the direction of x direction related to the base frame? So x direction will be opposite to that of the previously given. So the new x axis will be the negative x. The new y axis will be negative. So This way you need to solve this kind of a problem. Coming to the DH parameters, so here is a DH parameter. So we need to find a DH parameter for a spherical ZYZ wedge joint. So what is wedge joint? So this spherical wedge joint are generally located at this SCARA or a SCARA robot. So at the end effector, they used to locate this wedge joint. Okay, at SCARA robot or at maybe at Stanford manipulator. So at the gripper, they generally attach this kind of thing, which is kind of a wish simulator, and this wish has the rotational part. First is the pitch part, then there is a yaw, then there is a roll. Okay, so in this roll, you will find your gripper, thing like this, so that it can yeah, so that it can manipulate, or it can hold any object precisely irrespective to its orientations. Okay, so this is the transformation. It is this which manipulator is going through. The first is yaw, second is pitch, the third is roll, and you need to find the DH parameter. Okay, so first we in DH parameter, first you need to locate Z naught, the Z axis, right? So since this is all three are rotation thing, so the axis along which it is rotating, that will be your Z axis, right? We'll start with Z naught, which is your base frame. Since this is a yaw direction, Z naught, and this is a pitch direction, this will be Z1, and then there is a roll, which is Z2. Okay, and I think I have not mentioned there is a gripper also here. So the gripper will be along the same direction, which is, and this is sliding direction, and y3 this is another direction. Why I have chosen y3? Please go through the lecture. Okay. Now after choosing Z0, you need to choose X0, XI, right? And XI is basically something like choose XI by XI minus 1 ZI. Just cross multiply stuff to get the direction of XI. Okay. So, so the Z0 don't need to find. You can arbitrarily set X0, Y0, anything, but please do follow the right hand route. Okay. So let's when I is 1, x1 will be equal to z0 cross z1. Okay, so this is your z0 and this is your z1. So when you use your right hand thumb rule, you will get direction for x1 like this. So this will be your x1, right? And similarly, you can do it for x2. X2 will be the cross multiple of z1 and z2, which will be this one x2, and y3 you already know, and y1 you can easily calculate by using your right hand thumb. Since you have calculated the frame, each frame, then uh, you can start naming O naught origin. Like this is the O naught is the fixed frame, O1 first frame, second frame. So now let's start filling the DH parameter. Okay. So first, these are the DH parameter, which is alpha A T I theta, right? So theta you already know, because this is a spherical joint. It has all three rotation and it has three joints. So you can easily fill it theta 1, theta 2, theta 3. Now there is also a D3 which I have. So when you go from a raw to yaw to roll, there is always some kind of a distance has been taken, right? So this distance has been taken to implant this gripper. Okay, so D3 you need to also need to take care, right? First, because there is a difference in also alpha needs to change at every place. So please be careful while you write something like an alpha. So let's go through how alpha be calculated. So you need to measure, it's an angle between zi minus 1 and zi measuring about xi. Okay, so put I equal to 1 because what we are doing, right? When we put I equal to 1, it will be z0 cross zi, z1. So when you put z0 cross zi, what you will get? Uh, yeah, so it's an angle between zi minus zi. So measured along. So this is your x1 and this is your distance. So zi and z1. Okay, so when you do something like a through right hand thumb rule, you can easily calculate that there is a difference of 90 degree between z0 and z1. So I've easily put it 90 degree. Similarly, when you do it for z2, for frame 2, alpha 2 will be 90 degree again because you are calculating along this x2 and you see z1 and z2. What is the difference? Uh, there is a difference of again 90 degree, and for z2 and z3 there is no difference. So this is, and d3 can easily calculate. D3 is the distance between origin, so it is measured along zi minus 1, right? So you put I equal to 3, I think zi minus 1, how d, so d3 should be here. So this origin O naught, O1 and O2 are the same actually because there is no distance one here. This so Z naught, Z1, O naught, O1 and O3, O2, all three are having the same origin. Okay, let's move on to the next question. So this question is about the dynamics part. So let's just start this question. I think first read out this question. What this question says. I know this can be a lengthy one, but these are very simple questions. Okay, we don't need to worry about it. I am solving this big question because in the final exam they won't ask you solve the whole thing. Okay, but they can ask you a bit part of it. I mean, bit by bit. So you need to know the steps how you need to solve this. So instead of asking for like this, solve the fill the DH parameter, they can always ask you what is this D3. So you, or what will be alpha 2. Okay, so like 90 degree. It can be a multiple choice kind of answer. Okay, so you need to understand this, like how you need to solve this kind of questions. So the so first read out this question. So let's read out this question of point. So the uniform link of fully actuated PR manipulator. This is a PR manipulator which is prismatic joint and is a revolute joint. Having masses M1 and M2 and link length L1 and L2 respectively. The center of mass L1 is located at Q1 from the origin and link 2 is located at distance D from the joint with link 1 as seen in the figure. So yeah, so this is Q1. So this is actually 1 and this D is already given. Center of mass of that link from the connecting point. Let L2 be the let I2 be the inertia of link 2 about its center of gravity. So I2 is given here. I think it should be I. Yeah, so there is no need for this one because it's only translating. There is no need for inertia. For this one, you need inertia because it's rotating. So derive the equation of motion for this manipulator using Lagrangian formulation. Force F is in the direction of Q1. Q1 is the joint coordinate, the generalized coordinate, the prismatic joint, and Q2 will be the prismatic, the generalized joint coordinate in revolute joint. Basically, Q1 is like basically D, which is changing, and Q2 is basically theta. So there are two terms, which is force and torque term, and you need to derive this equation. So for this kind of equation, you need to solve this equation using a Lagrangian Euler method. And in order to solve a Lagrangian Euler method, you need to find kinetic energy and potential energy, and how to get potential energy and kinetic energy. You need to find first of all the center of mass of each link coordinate, and using that center of mass, you need to differentiate that center of mass position to get velocity, and from that velocity you can get a kinetic energy. Okay. So let's look at link by link equation. So this is a link one equation, and you see Q1 and DC1 is this is how the link coordinate has been given. So first we look at the center of mass for link one, which is Q1 0, because y coordinate is 0. When you differentiate this thing, you will get Q2 dot, Q1 dot, and 0. For link 2, it will be x2, y2, and how to get the x coordinate, Q1 plus dc1 plus dq, d cos q2, and the y axis here is basically this part, right? Is d sin q2. So again, you differentiate this to get a velocity component of x and y, right? So you got the velocity. From this velocity and position, you can find out the kinetic energy. So the kinetic energy of so you need to add kinetic energy of first and second link, right? So this is the kinetic energy, the first part. So half m1 plus half m2 vpc2. And since the second link is a rotational link, so we need to add some kind of a rotational kinetic energy, which consists of this thing. Right? So this part, yeah, Q1, right? Q1 is basically it's d dot square, and this velocity term is replaced by squaring this term, right? This has two terms. So velocity will be equal to dot square plus y2 will be is equal. This is what we have did here. We have did the we have squared this term, and when you square this term, there is a cos term, sine term, square, cos square, get added up and to get one, and then the sine. So ultimately, you will get this kinetic energy and the kinetic energy. And coming to the potential energy, there is only one potential energy since the link one is at the origin. So you will get only em2q sine q2, right? Because this is origin, and it is coinciding with origin, whereas this part is e sine q2, right? So that's why you get potential energy here. And since you get the kinetic energy and potential energy, you need to find out Lagrangian, and Lagrangian is basically kinetic energy minus potential energy. And just take this term and take the minus term. So now to find out the fourth equation, you need to apply the Lagrangian Euler equation, which is this equation. And you got the Lagrangian, and for link one, you need to choose q1 dot, right? And when you do q1 dot, when you put here, this what you will get. Again, differentiate. So please do remember it's a partial differentiation. You need to only take those terms which contain q1 dot, right? So there is this q1 dot is there, right? There's q1 dot here. There's q1 dot here. I think there is one dot here also. But please do remember there is q2 dot. Okay, so this will be 0. It is partially differentiating, and again this will be 0. Okay, and you need to differentiate with respect to t, and this is what you will get. And yeah, this part is over. This is what you will get, and dl by dq is 0. Why it is 0? Because there is no q1 term. There is, no, there is no q1 term. There is a q2 term, but there is no q1 term. That's why it's 0. When you yeah, when you apply this in the final equation, this is what you will get. So you have the first force equation. And similarly, when you do it for link 2, this is what you will do. Instead of q1, you need to replace it with q1. One need to be replaced with q2. Okay, so it should be q2 dot, and again you do the same thing. Here you will find del by del q2, the q2. So there is this q2 term. So when you differentiate with q2, we cos q, then there is a q. Yeah, there is only cos q2. There will be not q2 dot term, and then there is something like again a q2 term here. So this sine q2 term is there. It will become cos q2. And again you do the same thing. This is what you will get, and you will get something like a this equation. And this is the second equation. So these are the torque and force equation. This is what the objective of the question was. Need to find out the force equation and all this. Okay. Now let's move on to the last question. Question is about the Jacobian. Okay, so I know that I think there's a long formula for Jacobian. Don't know if you can mug up that big formula or not. But you need to remember that I think that will be a big formula. But there is a shorter way to solve some. But for that you need to. I mean, yeah. So please do remember that. Don't remember some big formula. Okay, if there's a big formula, then we will provide you the formula because I think the examination idea is not to check your memory power, they check your concepts. Okay, so fine. So this is the question. Find the Jacobian of this manipulator if the direct kinematics is given as this is a direct kinematics, which is basically the position of this end effector at. You can see there is a px, py, pz. The position of this point has given here, which is q3, c2, c1. Okay, what is q3 here? Okay, q3 is basically b, and this is q, and c2 is cos theta 2, cos q2, and c1 is cos theta 1 or q1. Then there is a d1 term. So this is given it to you, and you need to find out the Jacobian of a manipulator. Okay. So when the question say find the Jacobian, you need to understand what is the definition of Jacobian. Okay, so Jacobian is basically it's a linear mapping between uh, a small change in input and output, right? That's a that's a physical definition what it say. But basically, if you have something like uh, say the transformation matrix, right? The transformation matrix uh, tells you the end effector position. You can easily get it by using some kind of a transformation, and theta is your. So this is a Cartesian space, and theta is your joint space, right? And this is the transformation matrix. And when you do something like a small chain delta x, you will get something like a Jacobian here. It will be delta theta. When you differentiate with respect to delta t, you will get something like x dot. This is what you will get. X dot. This is Jacobian, right? So you have this x, you have this theta, right? How to find Jacobian? This is what the Jacobian, how Jacobian look like. So if you have delta x, delta y, here it will be delta px, delta py, delta dz. Basically delta f 1 by delta q, where delta f is basically your t, right? It has, so this will be your f1, your f2, your f3. You need to differentiate with respect to q1, q. So here they are q1, q2, q3, right? So it will be something like 3 cross 3 because there are three things, right? So it will be something like this. So you can use this formula, and when you partially differentiate with first, you need to partially differentiate with respect to q1. So q1 is cos theta q1. When you differentiate with respect to cos q1, it will be sine, right? So it will be sine 1, and then there is a minus sign also because we are differentiating. And then again, when you differentiate with respect to theta 2, which is q2, and again there is a sine 2, and when you differentiate with respect to q3, uh, yeah, it is the q3 will be gone when c1 will be there. Okay. This thing is called your Jacobian actually. Okay, in this manner you can get it. Okay, but in multiple choice, what they can ask is, uh, what will be your what will be the determinant for Jacobian, or when q3 is let's say 3 is 1, 1 is 45 degree, and q2 is something like 90 degree. So in that case, you need to put those value and calculate the determinant of a Jacobian. So that can be asked as a one of the multiple choice questions. Okay. So please do remember how to solve this kind of a question. I think yeah, this is it. This is all these are the question plus. But I have also left some questions which you can. I mean, one thing I think you should also try to solve questions from artificial neural network. I think one problem is already solved by professor. But what you can do is like I think I've also solved one problem for you. You can always go to the problem solving session document presentation. So I've uploaded in the at in the Google in that sheet. When you go through those sheet, there will be a for a Google. There will be a link for the there is a link for a Google folder where you will find those presentation link. So where I have solved one problem. Please also go through the one problem for for artificial neural network, because I think it has been asked sign. I think yeah, the neural network problem. Please go through this problem. This can be asked. Okay, and what is Q symmetric? And I think yeah, I have not covered a question on controls part. So please always go through the control part also. What is PD control? How to what is light now stability? How to we have given a some kind of a how to get a control law, and is that control equation, is that a control input, that input is light now stable or not, is it asymptotically stable, is it absolutely, is it simply stable or is it unstable. So I've also solved one problem related to that, so you can always refer that question. Okay, I think this is it. Is also think yeah, I've already when you I think if you have any questions, please do email me. Okay, so you can always in the last lecture I have given my email ID. Okay, so if you found any if you are solving some, let's say, some question answers from any of the prescribed books, if you find any difficulty, you can always mail me that question and can give you the solution. Okay, so yeah, that's it for this year. I think yeah, you have any if you yeah, so if you found, is there any problem with my lecturing ability, or any if you find any problem with my so I've covered as much as what I've known, as what I've understood from the lectures and also from my experience. So if you so please also fill the feedback form. I think you can always fill the feedback form by going through this. I think so, and you can always me a suggestions. I think yeah. So there is a feedback form here. You can, in there is a suggestion or a feedback form. You can always give me. You can always give me feedback, of course, that I can improve. Yeah, I think I will check 5 mark question patterns. So Ramesh, I really don't know actually because I have given yeah, I was given exam year back, and I think there is a mix of question. I don't know what they are following now, but there is a numerical ability question, I think, which will carry more mark than a MCQ question. And I heard that they have also introduced something like a comprehensive type exam. So I really don't know what kind of question, but yeah, marks. I would definitely tell that there will be a 2 or 5, 2 3 marks. I don't know about 5 marks, but if there is a comprehensive based question, then we'll get a yeah. If it's a comprehensive based question paper, then you will of course get that 5 marks. The question paper can expect 5 mark question. Yeah, I think you can always give me a feedback at the end. And yeah, I mean, that's all I can do right now. Best of luck for your exam. I think I don't know when it's being scheduled. I think by next week onwards you will. But yeah, I think there's a book. Okay, okay. So this book is basically the combination of the lecture which you have been. But yeah, I mean, this is the last lecture, so I will also upload this. But okay, then I think I will stop here the recording.